Well, hello everyone, and welcome. My name is Frank Pizzalia. I'm a geomorphologist and a professor at Lehigh University, and I'm one of the co-conveners, one of the field trip leaders for the Field Conference of Pennsylvania Geologists being held in and around southwestern Pennsylvania, in and around Ohiopyle State Park. And it's my real pleasure today to be able to give you a little bit of an overview introduction in this presentation about the work that we've been doing in the Ohiopyle State Park area. This is one of two pre-recorded videos that could stand as introductions, things that you could watch asynchronously in your preparation for attending the conference. And so we get to do this twice, right? We get to do it once now while we're in sort of COVID lockdown, and then we'll get to hopefully do this all in person in 2021. Um, uh, the two different videos, the two different presentations, one focuses on specifically the Ferncliff area in Ohiopyle State Park. The other one is a little bit of a broader introduction to the geology and the geomorphology and the overall research goals that myself and my research group have been working on. And that's the one that I'm going to be talking about here. Let me stand to the side because these are the main players in this overall geomorphologic research that we've been doing in Ohiopyle State Park. I've been working very closely with Jim Shalis from the Pennsylvania Survey. Christy Lee, Ethan Kurek, and Adam Patching are all students at Lehigh, both graduate and undergraduate students, and they've done a lot of the hard work, a lot of the heavy lifting here. And I would be really remiss if I did not recognize all of the support that I've been getting from the Pennsylvania Geologic Survey, the USGS, which through an EDMAP grant has funded a good part of this research, and really very importantly, the state parks. And so Ken Bisbee, superintendent at Ohiopyle, and his whole crew, all of the folks that work with him, they have just been fantastic. I cannot tell you enough how much I am appreciative of the support that we have gotten from Ohiopyle State Park. This is a good crew down here, very supportive of geology and geologic research. So where are we in the world? Well, we're in southwestern Pennsylvania. We're just a little bit south and east of Pittsburgh. And on this slide, what you see is the general geologic setting. This is the part of the Pennsylvania State Geologic Map. Ohiopyle State Park up here is flowing, is developed along the Youghiogheny River, which flows across Laurel Ridge and Chestnut Ridge as it comes out of the Allegheny Plateau and flows north and a little bit west towards Pittsburgh. And so you can see this here. The white here is sort of the area of research interest following the Youghiogheny River as it comes out of the Ohiopyle region right here and flows up to Pittsburgh. There are some really important deposits along the Youghiogheny River. Some of them are very well exposed at Ohiopyle State Park, and that's what you see in this picture right here. And so our research is focusing on the deposits along the Youghiogheny River and trying to reconstruct the overall erosional incisional history of the Youghiogheny River as it cuts through the Ohiopyle State Park region as a way of understanding the overall landscape evolution and geomorphic history of this region. And in particular, we're really interested in a couple of things that some of the more dramatic topographic features that we see, and you'll see that in an upcoming photograph. It's the waterfalls, right? So the waterfalls themselves at Ohiopyle State Park, Ohiopyle Falls, lots of questions about how these things formed, how rapidly they're evolving, and those are some of the things that are inspiring our research. Now, if we just zoom out a little bit, many of you should recognize this. This is the Three Rivers region. Here is where the Monongahela and the Allegheny come together to form the Ohio. Of course, this is Pittsburgh. Here is where the Youghiogheny River comes in and meets the Monongahela just south of Pittsburgh. And the point of showing you this is that you can see some really interesting patterns in the topography. And this is some of the first order things that we notice when we're saying, well, how do these patterns actually develop? Pittsburgh itself, right, is very hilly. We all know that. And you can see these U-shaped, this big U-shaped feature running right through the middle of Pittsburgh. Well, that's an old meander loop, probably of the Monongahela, right? Now completely abandoned. And so you get the sense that these rivers are quite dynamic, right? You get the sense that the current location of the rivers is not where they've always been. And as they're changing location, they leave a record of where they used to be. And going in and discovering that record allows to give us a time history of where the river used to be, how rapidly it's changing, and we could interpret that in terms of the different landscape evolution processes that have shaped this part of Western Pennsylvania. Moving a little bit closer to Ohiopyle State Park and putting both the Youghiogheny, which is here, and the Monongahela into the same picture, this is just, this view is not too far from the town of Perryopolis, if you know where that is on the Youghiogheny River. And you can see these really distinct differences in the topographic texture, right? So right here, you can see stuff that's really quite smooth. This is an old meander loop of the Monongahela River. And you can see those over here as well, several different examples of old meander loops of the Youghiogheny River. So again, the rivers are dynamic. The meanders that you see today are not the meanders that the river has always had. The meanders are always shifting and evolving. When you go to this part of the landscape where the old meander bends of the river are preserved, you find these deposits. Like I showed you in the earlier picture, these deposits are collectively called the Carmichael's Formation. And it's a grab bag. It's many different kinds of facies that you'll see in the Carmichaels. Everything that looks like river deposits, things that look like lake deposits, things that look like deltas dumping into lakes, things that are largely colluvium. All of this gets dumped into something we call the Carmichaels. It was first described over a century ago. And we're really interested in trying to get into some of the details and trying to understand what are the ages of these Carmichael's deposit. Is it all one deposit with one age, or is it actually a range of different deposits with actually a wide range of ages? And so we're trying to bring some new data to bear on those questions. One thing that seems to be the case is that no matter how you slice it, what we call the Carmichael's Formation, and when we look at the topographic and meander bend history of these rivers, you can't get away from the fact that they're probably related to the formation of Glacial Lake Monongahela. And many people have speculated on this and they've published on this. They're probably right, okay? So if you're not familiar with the Lake Monongahela story, here is the general idea, right? You start with a pre-glacial drainage pattern where the rivers are flowing out of the Appalachians to the north and to the west and up into the ancestral Lake Erie Basin, probably out to the ocean through some sort of ancestral St. Lawrence system. The ice changes all that. So starting 2.5 million years ago or so, when Northern Hemisphere ice comes down into the United States, the ice comes down and it forms a wall, basically a dam. It dams up these rivers that are flowing north. It's going to reverse the flow of some rivers. It's going to play a very important role in developing the drainage system that we currently see. When the ice is here, you make this very big lake that you can see here, and this lake backs up into the already pre-existing valleys. And you can see that this would be a very good opportunity as to where you're going to put lake sediments dumped onto these old meander bends. And so this is, again, probably what is going on. Where we are in Ohiopyle State Park, okay, is right out here on this little finger of glacial Lake Monongahela that probably makes it to Connellsville, probably makes it just through the water gap at Connellsville up into um, uh, 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 Ohiopyle State Park, a couple of kilometers upstream of Connellsville. So we'd like to see, is there really physical evidence for that? We would suggest that, that's where it is based on about how high we think the lake is. And we should say what actually is controlling the lake elevation is right here at New Martinsville. This would be the overflow for that lake. So this lake would back up, fill up, fill up, fill up, and it would find a natural sill, a low spot to spill over, and that's here at New Martinsville. So the gap at New Martinsville, which is now what the Ohio River flows through, wasn't there prior to the lake. The lake fills up, it spills over that gap, and in fact, that is what carves the path for the current day Ohio River to flow from Pittsburgh and of course down along the southern boundary of Ohio. The elevation of that gap, okay, or the pre-incised elevation of that gap would tell us that the lake should have backed up into the Ohiopyle State Park area, not all the way to Ohiopyle Falls, but it should have backed up into what is the northern reaches of the state park. Now, the other piece of key data, key observations that we use to try to put this story together is something called the longitudinal profile of a stream. So this is just a cartoon of a stream-long profile. A stream-long profile is nothing more than a plot of the river length versus its elevation, okay? And the shape of stream-long profiles, the shape of virtually every channel profile on the planet is one that is concave up. So streams are steeper in their headwaters than they are down at their mouths. Of course, there are always exceptions to this, right? And there's some places where the streams are steep at their mouths, but that tells you that something is perturbing the system. The equilibrium or the steady state balanced shape of a long profile is something that sort of looks like this cartoon, okay? Now I'm gonna take this cartoon and I'm just going to reverse it, just going to invert it. This is the exact same picture, but I'm putting it this way because as we move forward in the talk, all of the long profiles I'm going to show you are oriented this way. So here's the same thing, just reversed its orientation. This is going to be Pittsburgh, somewhere down here, okay? Somewhere in the middle of this long profile will be Connellsville, and then somewhere up here will be Ohiopyle, and then this is the headwaters of the Youghiogheny River, somewhere high on the Allegheny Plateau. This is what the long profile of the Youghiogheny River looks like, okay? And so it's complicated. Down here, you could see down where the Youghiogheny meets the Monongahela, the Youghiogheny is really quite gentle, quite flat, quite gentle, a really low slope. And crudely, the Youghiogheny has this concave up shape, but there's these big steps in it, right? There's these big breaks. So if you look here, where I'm pointing, this is Ohiopyle. That's a really particularly steep break in the profile. And that is something that we call a knickpoint, right? So a knickpoint is a steep part of the river long profile. Knickpoints could be fixed on the long profile, perhaps because they're flowing over. There's a very hard rock there. There's some sort of local barrier that fixes that knickpoint, or they could be transient, right? And what I mean by transient is that they're just in the process of moving upstream through the long profile. They were born somewhere down here, and they're moving upstream. The Youghiogheny River has got examples of both, okay? And so that's part of our overall research is to discern these two different kinds of knickpoints. This thing here looks like a knickpoint, and it is, but that's a dam. That's the dam at Confluence, okay? So that's an artificial knickpoint. That's a human engineered knickpoint right there. But the other steps on the profile are real. And so the Youghiogheny River has several knickpoints. We typically look at these knickpoints as disequilibria features. The river will incise and try to erase knickpoints from its profile. to get to that smooth concave up shape. Now, the relationship of the long profile of the Youghiogheny and the nick point here at Ohiopyle and the lake looks something like this. We would say that the paleo lake level was something around here. Like I said, the upper reaches of the lake would start pointing up just and around the Connellsville area, maybe just a little upstream of Connellsville. But the rest of what's in Ohiopyle State Park, the rest of the long profile and the Youghiogheny River seems to be above the high lake level. And so there's two histories we're going to be looking at here. Is that, you know, what do we know about the evolution of the river channel in the context of where the Lake Monongahela? What do we know about the evolution of the river channel outside of the influence of Lake Monongahela? Do these things have any connection to one another? What are the times that we're talking about here? How old is Lake Monongahela? How old are the deposits, the Carmichael's Formation, that down here might be related to Lake Monongahela, but up here might not have any connection to Lake Monongahela? And so these are some of the main research questions, things that we're still in the process of fully investigating. And maybe by the time that we actually get together for the field conference a year from now, we will have all of at least our analytical numbers back on Carmichael's Formation ages, and we'll have some firm answers to these questions that I'm posing. So nick points. What are nick points? Well, this is a nick point. There's Niagara Falls, right? Niagara Falls is a nick point, and it's a very rapidly moving nick point. Niagara Falls is moving at about 1 meter per year. Okay, Niagara Falls is only about 10,000 years old. It's moved 10 kilometers through cutting the Niagara Gorge as it's gone. And even historically, you can see down here, these are the historic locations of the Horseshoe Falls. And so Niagara Falls tells us that rivers, particularly ones that are steep and have lots of water flowing over them, like here at Niagara, nick points are very dynamic features, and they can move quite rapidly. Okay, so the key thing here is the amount of water, right? So the more water you can pour over a nick point, the more erosive power you have, and that nick point will both recline in its steepness and move upstream on the river. And you can see that Niagara is a great place to illustrate that point. For the Youghiogheny, we could model that, okay? And so this is a somewhat busy plot, but let me go through the different parts of it and you'll see what we're trying to show. First of all, in blue, okay, so in blue here is the river long profile. That is the Youghiogheny long profile. And for reference, that this right here where this arrow is pointing, that's Ohiopyle State Park. That's actually Ohiopyle Falls itself, okay? Now, in these colors down here, red, green, and this dark green, these are 3 different estimates for what we call the response time of the river, which is described by this formula right here. The response time, or tau, for the river, based on how fast we would expect a nick point to propagate up the Youghiogheny. So in other words, if this big steep nick point that we have here at Ohiopyle, including Ohiopyle Falls itself, was something that started down by Pittsburgh, how long would it take this steep nick point to get to where it currently is at Ohiopyle State Park? And depending on how you parameterize this equation right here, and we have several different ways that we could parameterize that equation. There's several different observations we could make to calculate this K value, which is an erodibility term, the erodibility of the rocks, and this M term right here, which is the concavity of the stream. These are things that we can calculate directly from the long profile. And this term here, KSN, which is the steepness of the stream. These again are things we can calculate directly by looking at the long profile. Depending on precisely how we parameterize the K value and the M value, This formula, which contains area, which is the amount of water that's flowing over the nick point, will give us a prediction for how fast the nick point is going to migrate. And so I've just put up 3 different parameterizations here. And the fastest that the nick point will go is, well, not quite as fast as Niagara Falls, but pretty darn fast. It would say that the nick point following this dark green line would get from essentially Pittsburgh all the way up to Ohiopyle Fall, all the way up to Ohiopyle State Park in about 1 million years, right? Because that's what you can see right here on tau. If we parameterize it slightly different with a different K value, with a different M value, we would follow this bright green line, and it would tell us that it gets from Pittsburgh to Ohiopyle, here in about 3 million years, right? And if we parameterize it a slightly different way, it might take as long as 5 million years to get up there. So that gives us sort of a ballpark range as to the rate at which the nick point is migrating and how it might be related to the formation of Glacial Lake Monongahela. Notice that on these response time curves, notice that as you go upstream, the amount of time that it takes for the nick point to keep on migrating slows, right? In all 3 parameterizations, the dark green, the light green, and the red, as you go upstream, it's taking longer and longer for the nick point to keep climbing. And that's because there's less and less and less water as you go upstream, right? Remember, the amount of water that flows over the nick point is directly proportional to how fast it's going to move. So as you go upstream, the stream gets smaller, the nick points go slower and slower and slower. If you go to the Ohiopyle area, you see these spectacular nick points. There is Ohiopyle Falls itself, right? And if you haven't been here and you haven't seen Ohiopyle Falls, go and see it. Next year, you'll all have the opportunity. We'll be all here together looking at it. But there it is, okay? And Ohiopyle Falls, on the Youghiogheny, is not the only waterfall in the park, right? The park has several waterfalls, including a really beautiful one right here at Cucumber Run and another beautiful one here at Meadow Run. Those waterfalls are different. The one at Cucumber Run is really steep and it looks like this. The one at Meadow Run is spread out. In fact, it's a water slide. People all go water sliding down it. So it has a slightly different shape, but the nick point is there all the same. In this picture, the blue arrow is the direction that the Youghiogheny River is flowing. So the Youghiogheny River comes, let's see if I can do this. It flows in this direction. It comes around this big bend, and then it flows down towards Connellsville. This big bend is called Ferncliff. That will be the topic of the other video that will be pre-recording. But as it goes around this bend at Ferncliff, the nick point direction is opposite the flow of the river. So the nick point direction is following these red arrows. And very importantly, as the nick point is coming around the bend here at Ferncliff, it gets to the mouth of Cucumber Run and it bifurcates, right? Part of it keeps going up the Youghiogheny, the other part starts going up Cucumber Run. And when it gets to the mouth of Meadow Run, it bifurcates again. Part of it goes up Meadow Run, the other part continues on the Youghiogheny. And so in this way, these nick points are like waves of incision that are moving and propagating up through all of not only the mainstream, but also the tributaries to the mainstream. And that process is really nicely shown here in this diagram, because what you see in this diagram is a drainage basin with a nick point moving right to the mouth of that drainage basin. When the nick point gets to the mouth of that drainage basin, a wave of incision starts moving up through that drainage basin, not only on the main trunk, but also all the tributaries. And you can see in the next picture here, you can see this wave of incision moving up and, you know, carving a canyon and taking these high elevations and converting it to these low elevations. The other thing that the nick point does is shown right here. So as the nick point is moving up the channel, as you can see in here, it's leaving behind what used to be the floodplain of the channel up here is now left high and dry above the channel as a river terrace. Okay, now this gets really interesting because what we do as you go along the Youghiogheny River, and you find these old river deposits. Collectively, they've all been called the Carmichael's Formation, whether they are formed by this process or whether they were formed by glacial Lake Monongahela. Everybody calls them Carmichaels, right? And so the idea here is to recognize that this process will leave these river deposits behind. On a geologic map, they'll be called Carmichael's Formation. We want to get in there and actually try to discern which of the Carmichaels is because of this process and which of the Carmichaels might have something to do with glacial Lake Monongahela. And oh, by the way, they all might be related, right? Because in fact, if this knickpoint is here, because the draining of glacial Lake Monongahela caused the Youghiogheny River to incise, well then heck, the knickpoint is genetically related to glacial Lake Monongahela. And if that's the case, then there's a connection actually between the formation of the lake, the draining of the lake, the formation of the knickpoint, and then the development of these river terraces as the knickpoint is moving upstream, propagating upstream, and leaving these river deposits behind. Okay, so there's how you can see the very tangled web that we've woven and that we're trying to work out. Now, what do the terraces look like? They don't look like this. This is what good terraces really look like. This is a picture from New Mexico. And in this picture, you can see the bedrock, which is red, and then you can see the river deposits up here, which are brown. You know, in a perfect world, this is what we would hope and want to see along the Youghiogheny River, so that we could map out these terraces and we can sample this material, right? There's a lot of vegetation, as you know, in southwestern Pennsylvania. And so we're really desperate looking for good exposures. The really good news is they exist. And so we don't have something quite as spectacular as this, but we do have this. So this is right along the rail trail, right? So if you go along the Great Allegheny Passage Rail Trail, south of Ohiopyle State Park, actually you're in the park, but you're south of the main region, and you're headed towards Connellsville, you know, here's the bedrock. This is I believe this is some Homewood sandstone bedrock. And the bedrock, right on top of it, you can see the river gravels. There's one right there. There's one right there. There's one right there. This is a beautiful example of the erosional contact between the bedrock and the river gravels. And we have found this time and time again. And so we're in the process of making a geologic map of these terraces so that we could see where did the Youghiogheny River used to be, both in elevation as well as laterally over its history, and how do this record of the terrace deposits tell us the genetic connection downstream to glacial Lake Monongahela. Here's where the park has been instrumental in really helping us here. I gave this little talk to the park back in July, or an early version of it, and said, you know, we have a couple of places where we think we can see deposits that we would really like to date, these old Carmichael's deposits, but they're going to be really hard to dig out. The park says, we got a backhoe. And so here we go. The park did a great job helping clear this exposure for us. Here's Ethan Kirk, my grad student, in the pit. And what we can see is that down here, where it is gray in color, this gray material, those are lake beds. That's a little finger of glacial Lake Monongahela that has made it up past Connellsville, pointing towards Ohiopyle State Park. And then the stuff on top, it's river gravel, it's colluviated river gravel. It has a heck of a soil way up here, a big bright red soil. It's been in the landscape a long time. As you might imagine, we've sampled this stuff to try to get an age on it. We don't have that age yet, but we have it sampled, and it's out at the lab, and hopefully in a couple months we will know the age of this deposit. Really important exposure. It was really exciting to find it and get it dug out and get it sampled. Now, what do we actually sample? Well, here's an example of a river terrace. This is not along the Youghiogheny. This is in Washington State. But again, here's the bedrock. There's the river gravel. And so a cartoon drawing of that, here's the river gravel. And in this case, You know, there's a chunk of wood stuck in there. And of course, if you have wood, you can use radiocarbon. You know, here are the radiocarbon dating results. Radiocarbon is great for the first 50,000 years. So for some young terrace, some young deposit very close to the river, that might work. But for these older terraces, we can't do that, right? And these terraces might be much older than 50,000 years. And by the way, it's really hard to find organic stuff. It's hard to find things like wood in here. So what do we date? Well, we have some other things we can do, and it's called cosmogenics. Now, I'm not going to go into the whole details of cosmogenics now, but just know this. For very common minerals that we find in these terrace deposits that you find everywhere on the surface of the earth, the most common mineral, of course, quartz, which is everywhere, that quartz is getting bombarded from outer space by cosmic rays. And those cosmic rays are high energetic particles. They come down, they hit the quartz, they cause a spallation reaction that generates elements, in particular beryllium, beryllium-10, an isotope of beryllium that is radioactive in and of itself. And so in the minerals themselves, such as quartz, you will generate beryllium-10. The rate at which you generate that beryllium-10 is fixed because it's fixed by the flux of cosmic rays. So you know how fast you're making it. So as long as that quartz is exposed at the surface, or it's within about 2 meters of the surface, you're hitting it with these cosmic rays and you're making beryllium-10. You make the beryllium-10, it's radioactive and it starts to decay. So there's a balance between how fast you're making it and how fast it's decaying. And so in a certain sense, what's happening is that the quartz is like getting a suntan, okay? It's at the surface. The more you hit it, the more suntan you get. If you could remove it from the surface, the suntan will start to fade, right? Because the beryllium-10 is decaying away. And we take advantage of that to be able to know something about how long a rock has been exposed. And we can take advantage of that to know how long a sample of quartz has been buried. It used to be exposed, but now it's been buried and its suntan is decaying away. So here we are in this picture here. Here's Jim and my student Christy. We were sampling for exposure ages for using beryllium-10 for exposure ages. In this case, here's Christy working in the lab. We work with the University of Vermont, and there's a good cosmogenic lab there. And we've been getting back a number of results, both on exposure ages as well as samples that used to be exposed but are now buried. Those are particularly good for dating these terraces, the burial ages. And we can summarize what we've learned here in this picture. So this picture is the Ohiopyle area. This is actually the town of Ohiopyle. This is the Youghiogheny River flowing around Ferncliff, okay? And all of the different colors on here are the different Carmichael's Formation deposits that are found at different elevations and have slightly different textures. So it's a terrace map. It's a map of the river terraces, but it's also a map of these different Carmichael's formations. And this is the map that's emerging from Ethan Couric's work. It'll become part of a published EdMap project by about May. The upshot here, the key thing here is that in a couple of places we've been able to date, or we've been able to sample using cosmogenics to try to get an age. One of the most exciting results has been right up here. We sampled a good exposure of the Carmichael's Formation, and we found out that it's about 600,000 years old, crudely, 650,000 years old. That terrace has been there, that quartz was buried 650,000 years ago. And that deposit is approximately 120 feet above the river. And so we have incision rates here, the river, so we now know that the Youghiogheny River here is carving down at rates of like 56 meters per million years, right? And we know that now because of the age of the deposit and how high it is above the river. Similarly, because of the map, that exact same deposit, which is in this red color, is exposed right here at the town of Ohiopyle. Here, though, it's only about 30 feet above the river. So the incision rate here, the Youghiogheny River incision rate here is only 14 meters per million years. Now, what gives? How could it be so close to one another? It's going at 50 meters per million years here, and it's going only 14 here. How can that be? Well, in between those 2 points is the waterfall, the knickpoint. There's Ohiopyle Falls. And in fact, not only Ohiopyle Falls itself, but this whole part of the Ferncliff region, this is the very steep knickpoint that you see on the long profile. And so if you're in the knickpoint or downstream of the knickpoint, your incision rates look like they're fast, right? Because the knickpoint is in fact propagating up the river. If you're upstream of the knickpoint or the wave of erosion hasn't gotten to you yet. So the incision rates look lower. And this is what we can figure out by mapping these terraces and by dating them and by comparing them to where the knickpoint is and is not. When we put this whole thing together, we get a map, or we get essentially a cross section that looks like this. So here's the long profile of the Youghiogheny River in the location of Ohiopyle. We're looking just upstream of Connellsville. So 0 is Connellsville. And these are all the terraces that we've been able to map. We've projected them to the long profile, and you can see their elevation with respect to the long profile. Here are the terraces that we have dated. We have some erosion rates, we have some burial ages, and we're starting to get an age model to put our story together in terms of the long-term incision history of the Youghiogheny River in the context of this very steep and very aggressive knickpoint, which is migrating up the channel. In order to do that and understand how these knickpoints look, we rely on people like Jim, because Jim put together this beautiful geologic map of the quadrangle around Ohiopyle. And here is Ohiopyle and Ferncliff. And now we're looking upstream as the Youghiogheny River cuts through Laurel Ridge Anticline and goes all the way up to Confluence. And I show you this map because one of the important take-home messages is that the very steep part of the river, the knickpoint on the Youghiogheny, is currently right here at Ferncliff. And at this location, the river is flowing over the Homewood Sandstone, a very hard, massively bedded sandstone. So the knickpoint is short and steep, right? It's not exactly Niagara Falls, but it's a Niagara Falls-like knickpoint as it comes around Ferncliff. In the future, as that knickpoint continues to move upstream, it's eventually going to go into this pink rock here, which is the Mauch-Chunk Formation. Mauch-Chunk Formation is not hard. It's not massively bedded. In fact, what's going to happen at that point is the knickpoint is going to stretch out and become more gentle, and the spectacular waterfall is going to go away. And as the knickpoint continues to migrate upstream and cut across different lithologic units as it cuts across Laurel Ridge Anticline, it will sometimes find hard rocks, at which point the knickpoint will shorten and get steeper, and you'll get a beautiful waterfall. And then it'll find the soft rocks, in which point it'll stretch out and become more gentle and just be sort of a series of rapids, okay? The next time that it's going to look like it does right now is all the way up here at a place called Ramcat. If you've ever been to this part of the world, Ramcat is one of the put-in points for the whitewater rafting. When it gets up there, the knickpoint will be on the Homewood Sandstone again, and it's going to look just like it does right now. But this just gives you a sense for the dynamic nature of these features and actually the connection between the geomorphologic interpretation that we would make and the bedrock interpretation that Jim has made. So putting both of these things together is required in order to understand the landscape evolution of any region. So I appreciate your patience. Thanks for bearing with me through this somewhat long discussion, but these are our general conclusions of where we are right now. We would say that the Ohiopyle knickpoint in the falls, based on our response time modeling, is probably moving upstream something like 1/10 of a meter per year, okay? That might mean that for the waterfall, it doesn't look like it's changing much at all, but at some point you'll get a whole slab that will break off very quickly. The waterfall will step back. The long-term uh, the long-term geologic rate of that process happening, we think, is about 1/10 of a meter per year. At the same time, the river is also vertically downcutting, right? And it's doing so probably at a rate about 30 meters per million years. If you're in the Nick zone itself, it's going faster. If you're away from the Nick zone, it's going a little bit slower. But we have both the downcutting and the back wearing, and we could measure both of those processes as we map out the terraces and date them. And then lastly, the Ohiopyle, the Nick zone is an exaggerated example of this transient upward propagating feature. Whether it was related directly to the formation of Glacial Lake Monongahela is a little bit of an open question at the moment. We're still investigating that, but it stands as one of the possibilities of how we would genetically link the formation of that lake, the formation of the Nick Point, the creation of the Carmichael's Formation terraces, whether they're all part of the same overall story or not. Again, thank you very much for your attention, and we look forward to the questions and answers during our sessions in November. Thanks.